Well, yeah, thanks guys. Thanks Rutha for inviting me. And I'm gonna give you guys this talk today entitled Embodied Intelligence from Human Experience. And I'll say up front, I think especially because there's yeah, like just interrupt me at any time. And this can be it can be super interactive. I wanna talk to you guys about stuff that you think is useful. So just let me know what's interesting and we'll focus on that. Okay, so as yeah, I'm sure all of you guys know, robotics is very hard. I've spent much of the past 4 years of my PhD getting robots to do things that to us are seemingly so simple, like things that obviously like since I've been 5 years old could do super trivially. And I think that comparison is what makes it so clear because humans are so incredible, right? People are able to do such incredibly dexterous tasks with really minimal training. And oftentimes the concept of like scene level generalization is like truly trivial for people. And so I think it's really when you study robotics for a little bit that it becomes so apparent how incredible people are at these different tasks. And so, some might even frame the entire problem of artificial intelligence, as Richard Knight say, as the study of how to make computers do things, at which at the moment people are better. And so we can really think of AI as just closing this gap here. And so, while daunting, what's exciting is that this kind of means that humans contain the intelligence necessary to imbue inside robots. So this kind of helps motivate the framing of why we might want to learn from people. So a lot of domains have tapped into some version of this or another. So in LLMs we leverage data from everyday internet users that are passively generating tons and tons of data. For text we have an internet worth of text that people have written, and people have uploaded billions of captioned images online for strong vision models to learn from. And so, one hope in robotics is that maybe the equivalent is to learn from real people performing everyday semi-passively generated data of people going about their days. But obviously the question here is how, and there's a lot of ambiguity. So I think we'll start by formalizing what I even mean. So the thesis statement of this talk is that through the co-design of training algorithms and data collection systems, robot policies can acquire new capabilities from embodied human data. And moreover, the transfer of capabilities improves as training data scales towards wide distributional coverage. So since this is the thesis statement of the talk, I can pause for a moment. If anyone has any questions, feel free to shoot. Otherwise, we'll jump into it. All right, let's. I guess Ruth, if I can't see the room, so let me know. But otherwise, I'll keep going.
Yeah, sure, sure. Yeah, there are no questions here.
Cool. Alrighty. So this talk will have four parts. First, three parts, sorry. First, we're going to talk about methods to learn from humans, in which we're going to talk first about my work on Ego Mimic. And yeah, actually, this hasn't been the only work that we've done in this space. We've also kind of followed up on this with extending to mobile scenarios with Emma, or designing more capable algorithms to learn from human data, like an Ego Bridge. But fundamentally, we'll talk about like the data collection systems and algorithms necessary to even learn from human data. Second, to study this problem at scale, we need a lot of data. We can't, and maybe more than we can just collect ourselves sitting in the lab as PhD students. So we introduced this new large egocentric data set called Egoverse. Then finally, we'll begin to study transfer at scale. And so I've started to get to do this through my internship work at Physical Intelligence. So I'll talk about this work called The Emergence of Human to Robot Transfer. And so first we'll jump straight into ego mimic. And yeah, the point of this section is to just like talk about the methods necessary to learn from humans. So just kind of recapping in other domains, we have this like passively generated data, but 2 years ago in robotics, all we really like the real thing that was starting to work at that time was just teleoperation. And as you guys know, like teleoperation can it's great in that it has it's the exact captures the exact mapping that we're hoping to learn, But this requires many years of of active effort and data collection, and it's kind of a scalability bottleneck. And so obviously many people have asked, can we use humans as a scalable form of data for robot learning? And so we were far from the first people to ask this question. There's a ton of works that have been trying to use human videos, but the issue with human videos alone is that they only contain state. It's just a single, it's a frame of an image from a video. And so people designed a ton of different proxy objectives to start tapping into this data. For instance, people use like 2D motion tracks, like in track or motion track policy. People did self-supervised vision objectives, reward modeling, and designed hierarchical policies. But we felt this was fundamentally limiting because it really only, in robotics, we need state and action. And all of these were just trying to design some sort of proxy for action. So we introduce a new type of human data, which we like to call embodied human data. And the state is not just an image, but it's an image and a hand position. And your action is future hand positions. And so this now sort of like exactly matches the modality of data that you get out of a robot via teleoperation. So we're really trying to think of how do you sensorize humans and capture data from humans in a way that you basically have a teleoperation data set, except the only thing is that the embodiment is a human. So with this data, the question is just how can we collect and learn from embodied human data? And so thanks to simultaneous advances in XR, we found that these Project Aria glasses were a great solution to collect embodied human data. It captures these actions in the form of 3D hand tracks and observation, which is this front-facing RGB. But to make this data useful, we now need to bridge the gaps between human and robot. So first, on the hardware side, we leverage this like humanoid-esque robot with these naturally mounted arms to minimize kinematic gap, and to minimize visual gap, we use the same visual sensor on the robot as we do with the human. And so as a result, you can see that, the human data that we collect on the left really closely matches what you see out of a robot. Only difference is that one is hands and one is robot. And Ego Mimic, our algorithm, just enables seamless co-training on these two data sources. So at a high level, Ego Mimic co-trains on both human hand and robot data. So it basically, you take your visual observations and your proprioception. You first individually normalize both the proprioceptive values. We use an entirely shared vision encoder and policy. In this case, we use like ResNet and the ACT architecture that was popular at that time. And we have two prediction objectives. One is shared between both, which is 3D pose prediction, because both human hand and end effector have a notion of 3D pose. And then for the robot data, especially because at this point we were using a joint controller, we also have joint space prediction. And so what you can see here is that basically like 90 plus, I think it's like 99% of parameters are entirely shared between human and robot, which is very different from other architectures. And so then we then evaluated this on three challenging real world tasks. So we have this continuous toy and bowl task where the robot keeps picking up a toy, putting it back in the bowl, which requires like some fine alignment and dexterity to empty out that bowl. And this groceries task, the robot needs to fill up the shopping bag via this thin handle and place all the chips into the bag, which really requires a lot of constant replanning because that bag is constantly moving. And here to test bimanual coordination, do a laundry folding task. And for as a bonus for those late nights in the lab, we got our robot to make us pour over coffee. So pausing here for a moment, I think the fact that we're able to do these tasks is starting to show us and really get improvement from the human data, is showing us that through the co-design of the training algorithms and data collection systems, Ego Mimic can improve the task performance by using embodied human data. So we'll show that in a like the controlled study that shows this. So, we go and compare against some baselines. So, for instance, what we do is show that Ego Mimic with a combination of both human and robot data is considerably more performant than an ACT baseline trained on just robot data. So this is kind of showing you that to some extent, in a very, at least in a controlled setting, you're able to mitigate the need of some robot data by including human data. And not only do we compare against ACT, but we also compared against the Mimic Play baseline. And so I want to dig into that a little bit because it sheds some insight into what architectures make sense here. So in Mimic Play, for those who aren't familiar, the general idea is that human data is used to train just a high-level planner using future hand pose prediction, and this conditions a low-level control policy, which is there to actually produce actions, and this is trained on only robot data. And so the issue that we want to highlight is that there's no gradient flow from the human data into the low-level control. In contrast, in Ego Mimic, basically all these parameters are shared. So both all aspects of the policy are benefiting from human data. So this leads us to believe that direct co-training may offer more direct knowledge transfer than hierarchical policies. And so, yeah, we think that this formulation helped us have some really nice generalization capabilities. So you can see that we were able to take this robot all around campus by collecting some human data in diverse settings, and we were able to generalize to them quite nicely. And so then one really natural question is, how does, so it's obviously the thing that matters with human data is how well do things scale? So we started to study this ego mimic where we first trained a policy with no human data, then with half the amount of human data, and then with all the human data. And we see a really positive scaling trend here. So quantitatively, what happens is this. Up to 2 hours of robot data, performance scales pretty modestly. And so this is what happens when you add a third hour of robot data. And then one might ask, what would have happened if at 2 hours you collected human data instead? And here's what's happened. You see a really strong lift in performance. So there's a big performance delta here. And what we're trying to highlight is that that collecting, basically in this setting here, collecting human data was a lot more efficient, and especially because you're able to collect so many more demonstrations of human data in the same amount of time. So let me stop there. That's the end of the ego mimic section. I'll take any questions on that first.
You can go.
Hi, Simar.
Hey,
So yeah, just actually on this particular plot,
yes.
on the 2 hour mark, there's the ego mimic jumps from like I guess what the ACT was to like some other value. Like, are you using some additional data for that 2 hour mark as well?
Yeah. Sorry, it's this is the thing I wish I had. I wish I could go back and have fixed this, but basically the jump at that 2 hour mark is actually because Ego Mimic has an additional training objective, even with no human data, using the Ego Mimic objective of basically predicting both Cartesian and joint loss alone introduces some performance improvement. So that's why Ego Mimic, even at the with no additional human data, has some performance improvement.
Oh, interesting. Is that something that you actually observe like universally across policies, or was it like an artifact of your particular setting, robot that you're using, or something else?
I think it was most pronounced in this specific task. I'd have to go back and look at the table to see how big of an improvement it was for like the folding task and the groceries task. I think it was not as pronounced as in the task used here, which is the toy and bowl task.
Interesting. Okay.
But for what it's worth, I think you can really think of it as just like an additional co-training objective, like not just joint prediction, but also, or not just, just having both joint and post prediction is helpful as just an additional co-training objective.
Yeah, no, I was just wondering if I should add that as an objective to all my policies as well.
Yeah, it's
Uh,
actually, I mean, I think this is a common thing to do, even in training state-of-the-art VLAs, is to train both joint and post prediction. So, um, So actually, I think people have come to this conclusion that it doesn't hurt to do both, even on your same data.
Interesting. Okay.
Um, I had a very specific question here. What's the score here? Like the
Score
y-axis?
is the basically the it's like a notion of like number of points that you can get, where each point is like putting the toy into a bowl and then emptying the bowl in some time horizon.
Okay, that makes sense.
Yeah, so it's like it was kind of hard to it didn't really make sense to have a success rate for this, I guess, because you can kind of keep scoring more points. Um, yeah.
Just out of curiosity, do you have a result of ACT that uses both joint and post laws together?
If you think of it, that's actually basically just ego mimic.
Why is that? I thought ego mimicry
Oh,
was,
sorry. You mean the blue line with both prediction objectives without human data?
yeah.
Yeah, yes, that is the thing I should have done, but I unfortunately do not have.
Ah, okay, okay.
Okay, cool. Shall we move on?
Yeah, yeah, there are no other questions in the room.
Cool. Great. Yes, sorry. I unfortunately I don't see it's not showing me your guys' camera feed, so you'll just have to tell me what's going on. Cool. So yes, let's jump into to part two, which is a new egocentric data set, which we titled Egoverse. So Egoverse was a large collaboration between a number of institutions, and I co-led this with Ryan Ryan Vanamia. But it was not possible without the help of a lot of people from these different companies to all the wonderful collaborators at these universities. So okay, first, why do we need to collect more human data? There's already a ton of human data sets. There's all of YouTube, Ego40, Epic Kitchens. Um, and so the reason that we need to collect more data is because we want this form of um, egocentric human data or embodied human data. Whereas these are the old sort of form of just human videos, which only have like, state for images. And to some extent, these have sometimes have some other features, but they kind of it's sort of difficult to convert them into the embodied data sets that we were hoping to have. And by 2024, 2025, we were starting to see a lot of works increasingly relied on egocentric human data. So not just our own, but others coming out of NYU and coming out of UCSD, where we're starting to find promising recipes by directly using embodied human data. But so yeah, and all these data sets up until this point were, very limited in diversity, small, fragmented across labs, and difficult to extend. We had to solve this, and so we had some guiding principles in designing this data set. Concretely, we wanted, the largest data set of embodied human data that was made specifically for robot learning. And so this means we also wanted reproducible baselines across institutions. The data needs to be well suited enough to answer controlled scientific questions, but we also need enough data to start scaling things up. And ideally, we want this data set to be really extensible. We don't want people to keep recreating the infrastructure to collect ego human data. We want everyone to just be able to contribute here, and we want to be able to ingest all that data. So with that said, let me dive into Ecoverse. So Ecoverse can be thought of as broken up into these three parts. The first part is the data set itself. So on the left here, you can see what we call the flagship data. The flagship data is about 100 hours spread across these six tasks, which we like really clearly defined in sort of like in the same manner that you might like kind of spec out a task that you want to do for teleoperation. We did the same thing, but with human data. So we gave people specific objects to use and like reset conditions and tried to make things like maximally controllable. And so when you go and look at it, it really looks a lot like episodic robot data, but with human hands instead of robots. But that alone is not going to be enough to study this problem at scale. So we additionally have the freeform subset of Egoverse. And so to collect this, we collaborated with these awesome industry partners like Mecca and Scale to collect over 1,200 hours of data. And you can see that this is distributed over 1,500 tasks with categories like these like home logistic tasks, like packing a suitcase, or someone actually doing their job of packaging coffee, people cooking and cleaning, doing laundry, assembling hardware, all sorts of things. And so we really felt that this was like like the large scale diverse suite of tasks that we needed to study the final part, which will be to study human data at scale. And so not only do we, have this data, we made sure to give it the best annotations possible. So we have not only this the hand and head tracking that makes collecting embodied human data feasible, but it also has these dense language annotations, which our strong state-of-the-art policies are increasingly reliant on. So that's the data set. With that data set, we can start to dig into the actual study we did. So, I mean, one basic question that we wanted to ask in this study is like, does ego-mimic style co-training boost outer distribution performance across many labs? Is this actually reproducible? And so what we have here is three tasks performed across three labs, and we see this very consistent performance improvement from co-training on these out of distribution settings. So you can think of these as like settings where there's some new object or new placement, and yes, slight variations in the base tasks, where the robot data has never seen this variation, but the human data has. And so, while everything looks nice in that plot, doing this, in real life was very grueling because we're doing real world evals across three institutions, trying to control as best we can for strategy and the eval scoring that we're using. And so, yes, and so I'm really happy that we're able to do this across all three of these tasks and just see really consistent and clean performance improvements. So then after just validating that this co-training improves performance, we want to ask like what data mixtures are most effective for co-training. And so across all three tasks, we see that increased hours of human data, so like on the left side of the chart, results in the strongest performance. But beyond that, the difference between these first two bars is that the inclusion of this like 2 hour subset of human data that is highly overlapping with the robot teleop data is actually necessary to be able to leverage the Egoverse data. So the conclusion here really is that like an in-domain overlapping subset between human and robot is an important anchor to be able to leverage diverse data. And then finally, because of all the metadata that we stored in Ecoverse, we were able to answer some more nuanced like questions like how scene and operator diversity impact generalization. And I won't dig too much into this, but basically we were able to scale up things like do offline validation by training models on increasing numbers of demonstrators or scenes and studied scaling trends across these settings. Then finally, Ecoverse is also the infrastructure and collaboration. And so one thing we're really proud of is kind of our pipeline here, where we're able to take heterogeneous data sources. It can be human data from a new lab, robot data from a new lab. And we upload this all to common buckets on the cloud. They get processed every day and you can actually view it straight on the web. And this is open, like you could go on ecoverse.ai today and view all the data we've ever collected. And then from that data set, we can use filters to do local training on whatever subset you want. And so you can kind of watch this in action where you can go on this portal, filter down to a specific embodiment, specific task, and go and not only watch the episode, but then you can go and get the episode hash and the metadata. And this hooks up immediately with our training code and infrastructure to go and be able to load up this episode and immediately watch it and then subsequently train on it. And so we're super excited by the community response here. I think over like 60 people reached out from different companies and labs who want to now come and help and contribute data. So we're going to have our hands full dealing with that now. Okay, so yeah, basically to conclude, like Ecoverse enabled reproducible science, but also scale. And so thanks to that scale, we can kind of get to part three. And so in this work, I'm going to talk about my internship at Pi and this work titled The Emergence of Human to Robot Transfer.
Hey,
So
Simar.
oh hey, yeah, let's talk about Egoverse first before moving on.
I had one question there actually. So, you said you have language annotations for these videos, right? In Ecoverse.
Mhm.
Can you describe a bit more on how do you get these? Is it like human annotated or is it automated?
So I think that the common pipeline these days is a hybrid. It's you usually get a VLM to do the first pass, but that alone is usually not good enough, and then you get people to refine those predictions. And so these were provided by our partners Mecca and Scale.
I see. Okay. Makes sense.
Mhm. Yeah. I think maybe just on that point, I think there's a lot of interesting study to do on what the right annotations are. Like, do you like how specific do they need to be? Does making it more specific make your policy have better language following? These are the things that we hypothesize to be correct, but I think we should study and just haven't quite had the data to study it.
Makes sense. Okay. Yeah. Thanks a lot.
Yeah, of course. Um, okay, so then let us get to yes, this work, the emergence of human to robot transfer. So yeah, so when I was starting out my internship at Pi, besides our current work with Egoverse, a ton of companies began to pop up seemingly every single day to start collecting human data at a massive scale. And so obviously this was super excited and we wanted to tap into this. And it kind of leaves the question like, can we just, throw it all straight into a VLA? But the issue is that there is still, there's an issue. The issue is that there's still a gap between the setup that we had in Ego Mimic or in Egoverse, and I think just being able to throw all this data straight into a VLA. And specifically in Ego Mimic, we had these like small single task policies trained from scratch. They were highly sensitive to visual differences, so we had to like match the camera sensors exactly. And one thing I don't talk too much about with Ego Mimic is that we had to do that like it wasn't like super necessary, but it still helped to do this like additional like SAM-based masking on the human and robot to further align visuals. And the level of generalization we were seeing was relatively small to like new table colors or to new like slightly different object appearances, but certainly not to like new object shapes. And so the hypothesis here with this project was basically to say when you start from a strong pre-trained VLA, can we generalize over larger gaps than ego mimic with no explicit alignment at all? And so this would really ask, like, kind of tell us that we are ready to start ingesting, a lot of human data and scale things up. And so I think the rough setting that we have here is as follows. So um, over time, your data set coverage keeps growing, and that's this like inner orange circle of all the data that sits on your server, and and then there's this like yellow aura of things that you can generalize to given that data. And so as you keep collecting more and more data, both of these things expand. You get more data, but the set of things you can generalize to also gets larger. And I think the setting that we care about is tasks that are on the cusp here. What are these things that you cannot quite generalize to, given your current data set and best model? So that's what we did. We found these two very challenging scene generalization tasks where we needed to clean up a dresser or a kitchen in a kitchen that you've never seen before at all. Or here we want to do this busing task on a set of objects you've never seen. So you need to know to put certain objects in this busing bin and certain objects into the trash can. Or finally, we may even have some task language strings that you've never seen before. So here we introduce an entirely new task in human data where the human sorts these eggs by colors, whereas the robot has only ever seen picking up eggs and putting it into a single carton. And so the experimental setting here is that we directly take this data, capturing, unseen scenes or objects or tasks, and we fine tune Pio 5 with it, and we fine tune with a 50 yeah, we fine tune with a 50/50 mix of human data. Um, and yeah, then we evaluate it on these new concepts that were only ever shown in human data. And so I think the thing that is unique here is that no one at this point had ever, had shown that you can just take like this pure egocentric human video with no alignment whatsoever, put it straight into a VLA and transfer useful concepts. Oh, sorry. Yeah. So yeah, no one has shown this kind of like direct transfer before. Um, and so yeah, the question we were trying to answer here is like, from this strong pre-trained VLA, can we generalize over these large gaps with no alignment? And so this plot is here to show exactly that. Basically, across all four of these tasks, we see a clear performance improvement in the yellow bar by fine-tuning with embodied human data with no alignment whatsoever. Um, and sorry. And yeah, so I think the thing that's really exciting is that the yeah, this is like truly just like direct code training is able to transfer these new scene generalization, object generalization, and even to new like task semantics. And so you can kind of see it in action here, where the robot is able to go and sort out the white eggs on the left and all the brown eggs on the right. Whereas like the baseline model would pretty much like randomly place eggs into different cartons because it had just never been exposed to this new task of sorting. And similarly with this busing task, the robot's able to go and clean up this table of new objects that it's not seen before. And then we also do it on these two mobile tasks of cleaning up this completely this unseen apartment bedroom and the apartment kitchen. And we went and did some. I think after doing these, we sort of added this one additional task as well to really test something that was very dexterous. So picking up these tiny objects and even latching these lids here. And so while the human data in this setting is not there to like transfer these super dexterous capabilities, but it was able to transfer more of the high level semantics of learning where to place each of these different objects within the toolbox. And so you can see that it's basically able to combine like the primitive motion skills that it knows from robot data and these like high level semantic concepts from human data. And you can see in the bottom right, like without the human data, it's like it's pretty lost and doesn't place any of the items in useful places. So while this transfer is great and all, the key of this paper is actually to study something about the notion of transfer, and it's actually the claim that human to robotic transfer is an emergent property of diverse VLA pre-training. And so the experimental setup here is that we have increasingly strong pre-trained models. So a pre-trained model that starts with just pure polygemma weights, so no robot data, up to a pre-trained model with all of the robot data that we had at Pi. The baseline was to fine tune with just robot data, and ours was fine tuning with human and robot data. And we do the same evaluation on these unseen tasks. So the key question is, does the delta from the baseline to ours scale as the pre-trained model gets stronger? And we're able to show exactly that. What you see is that the effectiveness of code training with human data scales directly with the strength of the pre-trained model. And I think one interesting note is that that final tick there, the difference between 100% and 100% plus cross embodiment is telling you whether the pre-trained model had many embodiments during pre-training or just the two target embodiments. And so I think what's exciting is that showing that the inclusion, like having your pre-trained model be trained on many embodiments helps you start to form much more embodiment agnostic representations. Sorry, let me close this out. Yeah. Basically that the inclusion of cross embodiment pre-training enables you to start forming, or really just like you're able to transfer more from this new embodiment, which is humans. And so, yeah, one specific task that I might point out is this eggs task, which I think is particularly interesting because we find that just increasing the strength of the pre-trained model did not naturally cause us to generalize to this task of sorting eggs, which just wasn't really covered in the data distribution. But so you can see that the blue line is basically plateaued. Like as the pre-trained model gets stronger, it does not get better at sorting eggs. However, it gets better at it gets better at learning from human data. So even though the base performance is not getting better, the yellow line is improving, which is telling you that this pre-trained model is just more amenable to learning this task from humans, which I think is very interesting. And so then the question is why? Like, why does diverse pre-training actually improve transfer? And our hypothesis for this is that at when you have very under like no pre-training or very undiverse pre-training, the latent embeddings of human and robot data are very, very disjoint. But once you have a pre-trained model that is trained on a ton of data and many embodiments, there's a lot more latent overlap, which suggests that the model is forming embodiment agnostic representations. So you can kind of think that once you've seen 10 embodiments, the model's like, okay, no worries, this is just an 11th embodiment, and I know how to deal with this. So I think the long and short of this paper is that we find that human to robot transfer emerges with the scale of robot pre-training data. And so I'll stop for there with the moment.
I have a question. So maybe I have missed, but what was the objective for the human data? Is it a joint, like, is it a pose error?
Sorry, the objective for the human data is actually very, very similar to like in ego mimic, where you're also just doing future end effector pose prediction. And in this case, all of these models are evaluated with end effector based control.
I see. How can you know the ground truth, like, pose, by the way? Is it
Of
possible?
the human hand.
Yeah,
Yeah, so this is using like various a lot of people have now developed these different like hand pose estimation algorithms from Ego Video, and they all use some form of some learned models that run from RGB, sometimes depth, kind of whatever information your sensors can capture.
I see. Thank you.
Yeah.
Oh, and by the way, for the earlier videos you showed, I think the human demonstration video, um, for those videos, the human hand was quite like unnatural. For example,
Mm.
a page like 114.
Yeah.
Yeah, is it like intended or have you tried with some natural like
Yeah,
photo?
yeah. This is a great question. I think it's something that I'm still really thinking a lot about is that so I think for the so in this work we didn't try sort of a more natural motion. The reason that we asked the operator, so really what we asked the operators to do was keep their hands in frame. And so and as a result of that, I think a lot of them kind of took this less natural motion as a side effect, which is sort of interesting. It's because it is very important that like the person's hands are actually captured in the video, which is and that's kind of limited based off of the FOV. So this in this case, this is using the iPhone, which has good but not like perfect FOV. So as a result of that, we kind of had to ask them to like make sure that their hands were visible and then sometimes I think the operators take it an extra step and do make these like claw hands and kind of pretend to be a robot a little bit.
I see, I see. Thank you.
Mhm. Okay, so let me continue. I just have a few more slides on this work. So we actually did a few ablations. I think one you might find interesting is this target robot ablation. So one might ask, how does collecting human data for a task compare to collecting like robot data from that specific robot? And these are roughly but not perfectly controlled for like number of demonstrations. Um, and you can see basically across the task, so like for this busing task, there was actually a decent bit of improvement, like pretty big delta between human and target robot data. But for many of the other tasks, it was actually very similar, where collecting ego human data was roughly as good as collecting target robot data in that setting, which I think was very exciting. We also compared collecting human data to collecting data on another robot. So basically, to answer the question, does human to robot transfer scale similarly as robot to robot transfer? And you can see that I think it's something that we should definitely test on a larger scale. But in this specific task for this busing, which we readily had data from both embodiments, we see that the human data is perhaps a little bit worse, but comparable to collecting UR5 data for the same task. And one final ablation, and then we can go and talk about some of these, is basically we wanted to study where transfer was happening. So here, actually, one thing I should have noted was the predictive objective for human data is not just pose prediction, but it's also subtask language prediction. So if you're familiar with PyO5, there's this like language subtask prediction objective, which is basically converting a high level language request to the more atomic, low level language of what the robot should do next. And so this is ablating whether we're getting transfer from the high level objective or the low level objective or both. And I think what's interesting is that it's actually the combination of both that really drives performance the most. It's not just like telling the robot what you should do next, but it's some notion of how to do it as well. And so I think this has some like kind of as a whole has some interesting implications. So obviously, so Yuka had this really awesome talk a few years ago, which I think really aged very well with this kind of like highlighting what the data pyramid of robotics is going to look like and how we're going to have different sources of data, and we have to kind of deal with the fact that each has some inherent limitations to their scalability. But I think one thing that I didn't expect is that I think this work actually suggests, to an extent, that there is, we actually kind of have to flip this pyramid on its head. And the reason I say this is because I think it turns out that you need some minimal amount of real world data to actually be able to leverage more diverse sources. So just having human data without enough like actual target robot teleoperation data is very poor, which you saw like in the early parts of those scaling curves. But once you have really diverse teleoperation data on the across many embodiments, then you're able to leverage more out there data, like from human videos. And I think it doesn't, I don't think this will apply to only human videos. I think this trend will apply similarly to using synthetic data or web data. So yeah, that's actually yeah. So actually, this is pretty much the end of the talk. We were able to talk about first methods to learn from human video data. We presented a new data set to begin to scale things up. And I presented my first, kind of the first work at attempting to study this problem actually at scale. And I think where I'm really excited to go next is kind of not only studying in the setting of scaled up robot data and with strong VLAs, but to finally get to the realm of studying very, very large scale human data and how to effectively pre-train on that. But yeah, that's the end of the talk. Thank you guys so much for inviting me, and yeah, I'm happy to answer more questions, especially on that last section there.
Thank you. Uh, Okay, I can go first. So I really like the part where you suggest, okay, increasing the model capabilities helps in better transfer from human videos. Uh, but I use like hinting towards something like you need strong pre-trained model on robot data and then incorporate human data, or that's not something you're
Yeah,
suggesting.
I'm not suggesting that there's kind of like a dependency in the ordering there. In fact, like what I would imagine is that you will just have some big mix where by like number of hours of data, it will be, much more human than robot But I think I'm saying that there's this necessary minimal amount of robot data. Like the more of that robot data you have in the mix, the better you'll be able to leverage these other sources. But not saying you have to do one, then the next.
That makes more sense. Thank you.
Yeah.
I guess like I have slightly more like general like broader questions. So, given your experience with human data,
Mhm.
and I thought I'll just kind of quench my
Please,
curiosity.
yeah, yeah, yeah.
But essentially, like, okay, I guess firstly, like, human data is actually transferring what kind of capabilities to the robot? I guess primarily, whether it's like towards, do you think whether it's like more dexterity or more like semantic understanding? I guess like you have that, whether it's high level or low level. But
Mhm.
I'm just trying to still kind of like figure out whether like we're actually learning new skills or whether we're like I guess in the eggs task, I feel it was more about understanding what eggs to put where, not really how to do
Yes,
it. So I guess
absolutely. Yeah.
uh,
Yeah, there's this is a great question. Um, Let me say a few things. So one thing I'll say about this eggs task, for instance, is that I 100% agreeing with you that what it really learned is like, yeah, what eggs do you need to put where? If the robot data did not have the primitives of how to pick up and place eggs, this data wouldn't have helped. I think what is interesting though is that it's both objectives that were important. It was both the future language prediction as well as the low level pose prediction. So it actually means that having this pose prediction objective is helping with the semantic transfer as well. Even though it was not a dexterous transfer, the pose prediction objective was useful. I think that's one interesting thing. Um, Another interesting thing, I think, if you take a step back outside of like just my work, because I think one thing about this work is that these are all it's all human data to parallel jaw gripper robot. This is an especially hard setting. And I do think we'll continue to get better at this. But maybe one setting that gives us like a bit of a sneak peek on what might be possible is like I think probably looking more out of the some of like the recent work out of NVIDIA, which is like for instance like ego scale, like which is looking at large scale human pre-training to dexterous humanoid robot transfer. You're able to see a lot more dexterity being transferred, where they're doing like these like one-shot tasks for very new tasks. So I think there's a lot of things going on. I think in order, maybe if you're trying to purely maximize the amount of dexterous transfer that you're trying to get, then yes, taking like additional inductive bias on like the actual platform that you're going to deploy on will also help. But I don't think that's going to be the case for everyone. There's a lot of people who care about parallel jaw gripper robots and more, cross embodiment generalist sort of settings, in which case probably the transfer that you're going to get from this data is more about generalization. And the last thing I'll say is that I think as the primitives get better for all of these models, because realistically, like, all these companies are going to keep collecting a ton of teleop data. Eventually, you're going to have covered most of the primitives that you actually care about, at which point a lot more of learning new skills is actually this compositional generalization and something that is a little bit more semantic level, which I think the human data will be able to help for a lot of embodiments.
yeah, no, that's a good point. I'm just trying to I guess you touch upon the point of like some target data would be helpful for learning like dexterity, like transfer from human to kind of the target embodiment as well. And I guess
Mhm.
kind of related to my second question as well, because I was wondering how much of human data would you say is equivalent to like 1 hour of robot data, for example? But I guess like it's kind of I guess in your last work, you kind of show that this factor also changes with how much robot data you already have, because if you have a lot more robot data, it's very easy to transfer. So I guess the utility of a single hour of human data increases as you collect more data. But I think I'm just trying to like kind of understand what you think where we are right now in this space, and how and do you think like it can be 1-to-1? Because I know in some of your results you're saying like it's actually 1-to-1 in some of the tasks, but like uh like how general is that? Like how many does that apply to every
Mhm.
task?
Yeah, very good question. The way that I'm thinking about this right now is that today it is like we're today from like an operational standpoint, it is possible to collect like truly very, very large sets of human data. So you're seeing like kind of all these startups popping up that are able to do this. It's not even that I think that the point is not like yes, well, one point which we should study in a controlled fashion is where does this break even happen? But it's human data is actually letting us collect data sets that we today could not collect on teleop alone, like these like many million hour data sets, because you're able to go and leverage so many different people, different companies that have networks that are able to do this. You're able to capture data in this very natural setting. Like we're able to capture data of people doing actual jobs. And so I think this is like kind of some of these additional benefits of like it's not even just that you need human data to be one-to-one as useful. It's actually just that it's also that human data lets you capture things that you wouldn't be able to just capture with robot data alone and at a scale that's much larger. So the fact that you can do so much more in such useful settings is like this sort of additional I think the additional thing that makes it so useful. And you're gonna I think ultimately this is what we're gonna do to curate like a very useful pre-training mix. Like we'll go through like tons and tons of data of people doing real economically useful things. We'll try to sample it really nice and uniformly to get really good task coverage, not over-indexing on one thing. And I think that's gonna teach us a lot of like, you know, the fundamental skills of like generalizing to new languages and these new settings. And so yeah, I think this is like more. So I think the question that you're asking is like really on like the what does human data look like for fine tuning? Like to get some specific capability, are you better off collecting robot for it or human for it? But I guess what I'm kind of saying is like there's also the setting of like human data in pre-training, in which case like that one-to-one parity is not what matters as much as like can you get this huge general coverage of data to construct a good pre-training mix? And I think that's like a lot easier to do with human data than with robot data.
Yeah, yeah, yeah. I think that makes sense. I think I'm kind of like trying to put it in the space of whether like if I want to do well in on a task that I already know, because I guess like all of you kind of end up collecting domain data for all these VLAs as well, like in domain data.
Yep.
I wonder like whether you should go ahead and like collect human data on it, like I guess
Mhm.
on that task, or like whether you should if you have the capability to collect teleop data, then you should just do that. And I guess it kind of depends on like how much more, like how much what is kind of the efficiency factor, I guess, of this
Yeah.
human data versus how quickly you can actually collect it. And it's kind of this interplay between these two numbers. But yeah, I think it just kind of
No, you're totally right. Like I think this is a question that people will start studying in the when you're thinking about I think this will come up with deployments. Like you are a company that serves a model and you want to go and like give some end user like a robot that, like does the dishes or something. I think so like what would one do to do this, right? You're some big model company and if you ship your robot there on day one, it might do okay, but it might also like, it might fail because it's never seen this person's specific kitchen before. So maybe a pipeline that could make sense is that um, like one is that if you're allowed to, yeah, go there, collect as much teleop data as you can, and then you're probably going to be pretty good at it. Like maybe teleop plus Dagger, plus eventually some form of RL. But maybe what you can do, especially because that's pretty intrusive to like the place you're deploying, they might not want you to like have to book out their kitchen for multiple days to collect data. Maybe the way you jumpstart it is by putting glasses on some people who work there. And then now you've collected some sort of in-domain human data, and that helps the robot bridge the gap a little bit. And then you do like and then you probably still need to do the dagger and RL steps on top of this to get to a really high performing model that like your customer is satisfied with.
Yeah, that makes sense. Thank you so much.
Thanks for your questions.
And I have a question. Like in the Ecoverse data set, I see like some of the data are like the human might move from one room to another room. Like the movements involve the movement of the lower body. And
Mhm.
but I see your demos, like most of the demos are just like the movement of upper body. So have you tried like transferring the movement of lower body, like the trajectories with lower body movements and like what's the performance?
Yeah, great question. So currently a lot of data in Egoverse. So we've done a lot of controlled study on the flagship data in Egoverse. Like we're very much actively working on a lot of the experiments for the freeform data. So we're doing things like pre-training on all the freeform data. We want to do more mobile experiments. So a lot of these are open, but I will tell you one thing that we have done, which is very similar, is we had this work, Emma, which was basically doing like ego mimic style code training on controlled data for mobile. So we saw something very cool, which is that in Emma, what you can do is we actually zero shot transferred navigation from human to a like a from like the navigation component from human to like a mobile Aloha style robot. So it turns out that like just by taking the slam head positions and constructing waypoint targets out of it, you could pretty much directly get one of these wheel-based robots to go and follow it. Um, so in that paper, we had this like scheme where navigation components were being learned purely from human data, and then the manipulation components were being like co-trained with between human and robot. So this is to say that I think transferring navigation may actually be on the easier side because there's like fewer embodiment specific. There's less embodiment gap because like moving from A to B is at least more similar between human and robot than like pretty complicated manipulation. Obviously, there's caveats here, like how a human goes and does something very complicated, like opening a door and stepping through it, will be pretty different, than the robot. But I think part of the problem is a little bit easier because there's fewer embodiment specific differences.
Yeah. Okay. Thank you. Great.
Yeah. So have you thought about the direction that uses the human data to inform the task, like as you said in the navigation task, like using the human demonstration as a context so that the robot can adapt to that task or like identify the task with only a few episodes, like meta learning.
Are you saying something like specifying tasks with like human data as like a prompt kind of, or like in context, or
Yeah.
um yeah, I guess I haven't explored this in depth. Yeah, I actually haven't really explored this much. Um yeah, I guess what I would say is that I think like currently where I've been most interested in is um because like I think yeah, I think to me, where I see the lowest hanging fruit is that I think a very scaled up human data will be the right pre-training mix. So I've been focusing most of my effort on thinking about how to do this correctly. How do you construct a balanced data set that like gives you a pre-trained model that is most amenable to learning some really dexterous tasks with robot teleop data and generalizing to new interesting language. But I think this is super interesting too. I just haven't explored it much.
I see, I see. All right, thank you.
Right. I think we're out of time, but thanks again. The fish pop.
Thanks, guys. A lot of fun.
Thank you.